This is 6.2a DTFS and DTFT. In this subchapter, we are going to examine some examples and properties. Let's focus on 6.2.1 first, where we'll examine the DTFS of a complex exponential and sinusoids by direct analysis. We'll examine what is spectral leakage. We'll see the solution of the synthesis equation by inspection, and we'll see that why the CKs are periodic in nature. Given the input xn is a complex exponential, this is the equation describing xn. Let's interpret it. It has amplitude of 3 and an omega of 0.2 pi radian at each sample. That means when we go from index 0 to 1 or 1 to 2, the complex exponential will move by 0.2 pi. That's why it's radian per sample is the unit. When n is equals to 0, there is a phase shift already. It will show you that when n is equals to 0, so we are sitting at j minus 0.5 pi. So there is a phase shift of minus 0.5 pi when we start with n equals to 0. So this is the polar representation. 3 is the amplitude, angle is minus 0.5 pi. Let us now plot this complex exponential. You can use the real and imaginary plot on the right hand side. In this, we will show you the real part with different n and the imaginary part. When n is equals to 0, we substitute into 3ej 0.2 pi n minus 0.5 pi. You realize that when n equals to 0, this is 0, so it's 3ej minus 0.5 pi, and this is actually 3 times cosine of 0.5 pi minus plus j sine minus 0.5 pi. Cosine of minus 0.5 pi is 0 over here, and sine of minus 0.5 pi is here, which is j1 times 3, so this point is exactly minus 3j. Now, so we have real part is 0 and minus 3j. So if you now look at this second picture here, this axis is the real axis, and here is 1 and here is minus 1. On top is j and below is minus j. So the first point, this is x0, is equals to 0 minus 3j. That is why this point is sitting below this vertical axis of the complex nut plane. And this is the real axis, and this axis coming out here is time. Because the omega is 0.2 pi radian per sample, at every sample that we transfer, you will see that it transfers by 0.2 pi here as well as here. As time progresses positively, the cosine will start to rise and the sine will rise from the negative 3j upwards. This will translate to a clockwise direction. So this point to this point is x1, this is x2, this is x3, and so on. So you'll see that the complex exponential is rotating anti-clockwise. And because the omega is 0.2 pi, it will take 10 samples. 2 pi divided by 0.2 pi, it will take 10 samples to complete one complete cycle. So let's count. x4, x5, x6, x7, x8, x9, x10. So x10 is sitting again parallel to this guy, which is at minus 3j. What about the 2D representation? This is x0, which is, this is the real line, this is the imaginary line, and we are sitting below the real line because we are at minus 3j. This is x1, 2, 3, 4, 5, 6, 7, 8, 9, and on the 10th sample it will complete one cycle. So this is the complex exponential 3e plus j 0.2 pi n minus 0.5 pi. We now remember that whenever omega is positive, this complex exponential is rotating on an anti-clockwise manner. The 3 indicates the radius 3, which is a circle, and minus 0.5 pi is the phase shift. It allows us to start from any point when n equals to 0 on this complex exponential circle. Now with that, our task is to find the DTFS. The DTFS because this is a periodic signal, and we now know that capital N equals to 10. So we need to find C0 to C9. Now, when we use the analysis equation, we can calculate C0, C1 until C9. Along here, we'll calculate the magnitude as well as the phase. Interestingly, the answer is that all the values are 0 except at C1. Okay, so that's the interesting observation now. This is the angle of C1, this is the magnitude of C1. So this horizontal axis is with respect to CK, where K will be equals to 0 to n minus 1, and n minus 1 because capital N is 10, so it's C0 to C9. Now, sometimes we'll ask you, instead of showing us the horizontal axis as C0 to C9 or Cn minus 1, we want to see the horizontal axis with respect to omega. So C0 will be mapped to the 0 radian per sample. Why is C1 0.2 pi? It is because what you will realize is that omega naught is equals to 2 pi over n. In this example, n is 10, and therefore this is 0.2 pi. You realize that every time we move by k is equals to 1, we are actually moving by 0.2 pi. So the k here is an index that goes from 0 to 9, will translate itself to 0 to 1.8 pi, because at the 10th sample you will be at 2 pi. So most of the time we write 1.8 with no pi because we are stating that the horizontal axis is with respect to the value times pi. So please remember how to translate from k, index k, into omega of radian per sample. All we are saying is that the horizontal axis is nothing but k times omega naught, or k times 2 pi over n. Okay, so the horizontal axis is written as k, but it's actually reflecting the real frequency as k times 2 pi over n along here. Now, when you plot DTFS using MATLAB, you'll realize that sometimes the phase is very horrible. It is there's a lot of random values, even though the magnitude is very small. This is due to numerical precision. So what I did to make it nice is to say that if the absolute value of the magnitude is smaller, or it is greater than a very small value, only when it is greater than a very small value do we show you the angle. Otherwise, this is set to 0. Okay, that is why all the angles here are 0 nicely. But in actual fact, if you write your own code, you'll see that there's some values here, although the magnitude is very, very close to 0. Now let's interpret this. Our equation is 3ej 0.2 pi n minus 0.5 pi. Why is this xn and this magnitude spectra related? Well, look at this. It says that at 0.2 pi we have a magnitude of 3 and a phase shift of minus 0.5, with no other signals, 0 being everywhere else. So the DTFS representation of magnitude and phase tell us exactly what the signal is. You can think of the DTFS, the coefficients, as representing the equations as sum of complex exponentials, because at values here we are talking about at different complex exponential, we are showing you what the magnitude and phase should be. In the next slide, we'll show you when we analyze, instead of using n equals to 10, which in this example is okay, we'll examine n equals to 100. What will happen? Thank you.